All right, good morning. Let's get started. So these are the grades so far. So we've covered up to 31% grades. And have you guys picked up the exams? The exams and the homework assignments and quizzes and all should be with the secretaries. We haven't get the programs yet, right? So most of you did very well on the exams. I think the average was 58.1 out of 60. The max obviously was 60. And min was 50, I think. But on average, most of you got it right. And I'll tell you in a bit one of my thoughts on one of the process, right? Before that, you got the email about the homework project, right? What you expected the thread programs to do, right? The sort of the graph, right? I hope that made sense, right? You know, as you go from one thread to four thread, you sort of expect it to go down, but you can't go below 1/4 of the stuff because you have four processors. You can't do it faster than 1/4 of the time, right? It's okay if it's not falling down like that, but it's not okay if it keeps going down below fourth, right? If your thread program took one time, you know, 1/3, half, 1/4, and then 1/5 and 1/6, and keeps going down, then something is wrong, right? Because if you only have four processors, you can't make it go faster than a quarter of the time, right? Because you need that much work done, right? So again, I mean, I think I don't have much to say about like sort of folks up there, but sort of like this. There's a bunch of people who are kind of falling off the chart. I mean, obviously the y-axis is not going to 0, but I'm not worried about that crowd, but this is crowd kind of like falling off, right? And that's not a good sign. You don't want to be in, at least you don't want to be in this curve, right? So if you're in this curve, I mean, we're already up to 30%, like less than a third of the grade, right? So this is not anyway looking as a final. But if you're somewhere here, you're making it very hard for me to give you a good grade, right? So, like, you have to do the right thing to move up above the stuff, right? I'd be a lot more comfortable if it's like that, where it's sort of gradually kind of falling off. Whereas the decision to give a grade is a lot easier because it's nearly hard for me to give an A for somebody here. So, right. So one of the things I noticed from the exam I think the question 4 on monitors, recursion, and deadlock, right? Many of you answered it in a fashion which is not exactly what operating system defined as a deadlock, right? Operating system defines deadlock as the four conditions have to hold, and if they hold and only if they hold are they considered deadlocks in the operating system sense. And that's the only thing I ask you in the operating system sense, right? In the English sense, if you look at the dictionary, I think the dictionary states that deadlock is when you can't make progress, right? If you can't make a progress, then it's considered to be a deadlock in English sense. And many of you use that interpretation to answer that you may go into infinite loop because your program may be buggy, that when you go through a recursion, you don't release some resources. And so your program can be buggy and it can keep recursing infinitely. So since it's recursing infinitely, it's in a deadlock, right? Recursing infinitely would be a deadlock in the English definition, but not in the computer science definition because it has to follow that four things, right? So if it is not, then, so don't confuse what you would call it in a colloquial sense and what you do from an operating system sense, right? To give you more sense of, so if your program goes into infinite loop, that's called infinite loop, right? And that's not a deadlock. That's infinite loop. That's a program bug, and we don't talk about that, right? To make it more concrete, what would happen if you ran this program? I created a semaphore, right? And I set the initial value to be 0, and I do a wait, right? What will happen? Remember the definition of wait, right? Wait tries, if it is 0, it'll wait for somebody to signal it, right? Because it can't go negative. So what would happen here? Yes,
It'll just sit and do nothing.
Yes. So which is kind of there, right? I mean, the English meaning says that it reaches a standstill or stalemate, right? It reaches a state where it's in a, yeah, you could argue it's a stalemate or standstill, right? Is this deadlock?
No.
Why not?
It's not like, it's just looping. It's not actually like
Yeah, but
another process. It's also stuck.
so you'll have to give your reasoning based on the 4 conditions, right? Remember, the 4 conditions have to hold for it to be a deadlock, right? So, yeah.
Something else can run while this is waiting, so there's no usual circular waiting.
There's no circular wait, right? Yeah, this, like, remember the 4 conditions, right? One is circular wait, one is hold and wait, one is mutual exclusion, and the other one, forget, right? So there's no circular wait here. I mean, it's just one thing waiting. There is no hold and wait here either, right? You're not holding anything. I mean, this process is not holding anything, right? It's waiting, but there's nothing it's holding, right? There's no circular wait. So by those definitions, this is not a deadlock, right? That doesn't mean that this program is fine. I mean, obviously, this is a buggy code, right? And we don't typically talk about buggy code. I mean, you can come up with very elaborate ways or very simple ways to come up with the bugs. So this is one of those, right? So this is not a deadlock. So none of the things you talked about deadlock happens, right? For deadlock, in the operating system sense, has to happen. You have to have all those 4 stuff, and this is not deadlock, right? So when people talked about recursion, they said, the program may be buggy, so it may not release some resources in the previous loop. So when it comes back up, which is similar to here, right? I mean, this is a very degenerate case of what people are arguing, right? But essentially, if you run into one of those, you're standing still but not deadlocked, right? Some of you answered it saying every time you call a function, so the new iteration would be a different process, right? That is plain wrong, right? So when you call a function, unless you fork or unless you do a pthread create, calling a function is not creating a new process, right? Does that make sense? When you call a function, you're not creating a new thread. You have the same thread. When you call a function, it's the same thread. Unless you explicitly do a fork or do a pthread create, you cannot create a thread by just calling a function, right? So when you call a function, including yourself, you're still the same function, right? You're still the same site, same thread. You're not causing a different one, right? And some of you said it's just not possible because of the way the program would disallow that, right? Because it's out of the scope and stuff, and that's not true either, because it's nothing to do with the scoping rules, right? If you do a monitor, it's just like a normal program. If your program allows recursion, that'll be here, right? So, but this is the main thing. So don't confuse these two, right? One of the things I bring this up is if many of you go for Java interviews and stuff, the exam you had is sort of what a lot of companies I know tend to ask you in the interview process, right? It kind of quirky, but kind of exposes whether you know these things, right? It exposes whether you know deadlocks. It also exposes whether you don't understand something else, right? Like mixing the notion of what deadlock is and what the English notion of deadlock is. So it's important that you understand this stuff, right? The same with any other stuff, right? If somebody says like, how do you do recursion? They're expecting a specific programming concept, not the English concept of what recursion is, right? I think Microsoft used to ask the question, can you unroll a recursion on the fly, write a program to unroll a recursion without recursion, right? So sort of like that, if they ask you, you want to be clear. Make sense, right? So there are a lot of stuff which kind of comes at you because I think it's something that you're supposed to have known somehow, right? I'm not sure who is supposed to have taught stuff like that, like the scoping rules and things like that, right? So as we go along, if anything was not clear, let me know so we can look at those, right? So So far, we looked at processors and how to manage those. The first module looked at how to give processors to your program. The second module looked at how you might solve some of the problems you create by having the first module, the offset of the first module. So the next two modules look at the other components, which is data, right? Your programs have to have a CPU or a brain, and it needs some data to manipulate, right? It needs some data which may be available on the fly, or it may be on the hard disk or something. So they may be persistent data, or they may be data that you do it on, you calculate in your program, right? So in this module, we're going to look at how to manage your memory, which is the sort of the temporary data. And next module, we'll see how we'll manage the persistent data, meaning data which will survive your programs, which is in your hard disk or what have you, right? So that's the goal here. So even though we don't talk about threads, we don't talk about processors and stuff, doesn't mean that this is completely separate, right? So one of the things we talked about when we talk about thread is there are two threads operating on the same program and operating on the different parts of memory. So that affects here, right? So threads are always in the background, multiple processors are always in the background. We don't explicitly state it, but it's there, and I'll try to bring it in as much as possible, right? Make sense? So in a very high level, let me tell you what we're trying to solve, right? The first one is your hardware has memory, right? I mean, you talk about, you have 4 gigs of memory, 2 gigs of memory, or what have you. So that means you have a chunk of memory illustrated by the top blank box, right? So you have this chunk of memory. And the goal here is to make sure that your program has something that it can run on, right? Since we talked about multiple processes, you want to run multiple processes where the multiple processes get to take some of these chunks of memory. So they're illustrated by this colored dot. So you have this big blue box, and hopefully there are 3 processes, each having its own set of memory, right? So the memory management module tries to make sure that you can run these 3 or however many applications you want, and that'll fit into this big memory. And it'll have to make sure that they are protected such that the red one does not have access to the orange one or green one or blue one unless you explicitly state it, right? So I want to be able to give each of the processes some chunk of memory, which will have to come from this larger piece of memory which may be in the system. And I want to be able to protect it such that whatever mistake you make may affect you, but not the others. So you want to be able to run multiple processes, right? And we will see that none of this can be possible without the hardware support, right? And we'll see what hardware support you need. But essentially, to provide this kind of support, you need hardware support. But our goal is to make sure that we can run multiple processes on the memory, right? And you want this to be transparent, right? So one step would be to say, you as a program knows exactly where you're going to be. You're going to be in the orange area, you're going to be in the red area, blue area. Or ideally, you don't worry about this. You compile your program, and magically, what we call linking, when you load or whatever, you do go through some process such that your program can be put wherever it wants, and you as a programmer has no idea, right? In fact, most of you never thought about, when you wrote a program, where in memory it's going to sit, right? So we'll see how that can be achieved. And so again, it's a partnership between operating system and hardware. Hardware has to give some facilities, and operating system manipulates some things to make these things happen. And the last one is, it's very restrictive to have something like this, where the colored bars are subset of the larger one, right? So if you want to do it in a simple fashion, you can have the whole memory and give it to different processors. If I have 3 ones, I can say, you get like a third, you get a third, you get a third. But it may be nice to actually run programs which are larger than what the physical memory is, right? And it's called virtual memory. We'll look into that. So essentially, even though you have 1 gig of memory, I can run a program which could take 3 or 4 gigs. And if I do things right from the operating system perspective, you as a programmer won't see too much of a program loss, a performance loss, right? So I can run larger programs in the memory you have, and depending on how I move these things around, you will be happy and things will be fine, right? And so that's the notion of virtual memory. We'll see that too, right? So the goal here is to see how you can take a program, map it into memory, and how you can do that such that you don't have to worry about where exactly it's going to go as a programmer, and extend that to say how I can run arbitrarily large size of programs onto the system such that you don't have to have the right memory, right? In fact, most of you use that. I mean, none of us have enough memory to run all our programs, right? Most of us have a couple of gigs of memory, and you run programs which take larger and larger space. And the way we do virtual memory is to move stuff off into hard disk and bring it back, right? You might have noticed that because if you have your desktop or laptop with not enough memory, whenever you do something, you'll see your hard disk go crazy because things are going in and out, right? And we'll see how you can avoid some of the stuff in notion of thrashing and all those things, right? So that's the super high level of what this module is meant to cover, right? And the thing to remember is, because of the hardware requirement, it has to be moved up the hierarchy for things to work, right? So the hardware defines multiple hierarchies. We mentioned this in the introduction, right? There's the hard disk, and then there's main memory. There's like multiple levels of cache, right? Your processor only operates on some things which are closer to it, and your goal is to move stuff towards the processor as much as possible, such that you get overall good performance. And we'll see more as we move along, right? So essentially the idea here is if your process is being scheduled to a processor, I want to be able to give as much memory for that particular process such that you not only get the CPU, but you have the memory in the right area so you can make good progress, right? Before I proceed, I want to give a brief overview of how programs are built, how programs are compiled, right? And obviously this is a course for compilers. But I think we need to understand in a little bit, and I think we can kind of go through that. Most of you have programs, so you kind of are aware of some of these procedures. I don't know if you can see from the back, right? So when you write a program, and the source program on the top, like the blue circle, you send it to a compiler, right? Your GCC or what have you. GCC, in fact, will convert your program from C to assembly language. Then from assembly language, it converts to object code, right? So that's part of the compilation process. So it converts that from something to an object module. You might have seen it as a .o. So if you take a .c program, it converts that to a .o program. And then you have to link it, right? If you, at the last step, which usually takes some time, it links it with your program and other libraries, right? So if you call printf, it has to load the libraries. Some of you might have noticed if you compile for the pthreads, if you didn't do the -pthread at the end, he'll say, I can't find pthread create or something. So you're trying to find all the libraries, put them together into this one program, right? And then once you have this program, you need to have a notion of a loader which loads this program onto the main memory, right? And I'll give some examples of what exactly has to happen. But essentially, you as a programmer never think too much about where exactly memory things have to happen, right? And as we go down the stack, you are adding more and more knowledge. The operating system gets more and more involved, right? So when it comes to here, the operating system gets involved. So it might tell you where to load your program. And based on where you're doing the program, your program may be modified in such a fashion that you're able to run, right? So the operating system says, okay, now I'm going to assign you to memory bank 43, right? It's going to tell you that now you have address from 43 to 1000, right? So the loading phase would change your program such that all the memory will look like you can still run on the assigned address. So that's part of the stuff. And this is also a location where you load dynamic variables, right? Dynamic libraries, sort of your DLLs in Windows terminology, right? Right? You had a question? Oh, sorry. So I'm going to take the simplest program, and even that creates a whole bunch of junk. I'm going to just show you the important stuff, and you feel free to run this on a Linux machine to see what exactly happens, right? I mean, Linux is easier to deal with. So I have the hello world program, right? You typically include a stdio.h, and you have a main program, and you say printf hello world, right? Sort of the simplest program, C program you can imagine. So I'm going to do a GCC minus v hello world.c. Right? Minus v tells me verbosely what it's actually doing on your behalf. And I edited stuff out because there's a lot more stuff. If you look at at what you do, it'll tell you where the libraries are, where the libraries should be searched, and all those things. So that's not really fundamental to what we're trying to do, I'm trying to show here. So essentially, your GCC goes through 3 steps, right? When you do a GCC, it does 3 steps in this case. The first step is to compile your program, which is called the compiler CC1, which is the first step in a compilation. It takes a program and converts it to an assembly language, right? I'll show you what the assembly language will look like in a little bit. So essentially, it takes a program, right? Forget what the dump base, arc base, and all those things, and it says minus o dot s, right? That's the assembly language program. So it takes your hello world program, converts it to assembly language program, and then it calls your assembler with a certain options to say convert the assembly language program to object code, right? Which is essentially that changes your program from source program to object module. So in the first top bubble to the next module, the next bubble. And then the last one is collect 2. It collects all the libraries and everything to create an actual program, right? And it has a lot more arguments than what I'm showing. But essentially it's saying, I want to create an ELF program, right? ELF is one of the mechanisms by which the compiler can tell the operating system, this is what I need, this is where the memory should go and stuff. So this is one format that this Linux knows. So it's saying, I'm going to create an ELF module, right? And I want to use dynamic link loader called LD Linux. So when you run the program, this LD Linux gets called, and that's going to load dynamically some modules. It's going to add a lot of objects which you didn't realize that it existed, right? So when you run a main program, there are other objects that needed to be linked into your program to make the whole program work. So there's CRT1, CRT-IE, and CRT begin, and CRT-end, CRT-end.o, right? We don't know what those are, but assume that those are all needed to convert from your main to actually run on the machine, right? And it's up to GCC to figure out what needs to be brought in and stuff. So it's bringing lots of objects which you didn't know existed. So even for a simple program like Hello World, it has to bring in lots of those stuff, right? And in a simple program, you use the printf, right? Printf comes from the standard input-output library, which comes from your standard C library. So it's actually calling it by saying it's including -l GCC, which means that link in with the C library. And then it's doing GCC -s, which means that I also want to link in the shared library, right? So part of the C libraries come to you in a static form. Part of it comes from a dynamic form. And the dynamic loader, which will be called to do this, is this. You also have LC, right? It's not very important to remember all the details of whether it's GCC or whatever, right? One thing to remember is the order is important, right? The way the linker works, the order of how you specify this is important. Most of you don't have to worry about this because this all happens on, GCC gives all this stuff for you. But essentially after all this stuff, your program now morphs from the simple printf stuff to have all the stuff that is needed for your program to run on the machine, right? Which is all the CRT business. Link all the C libraries that you need for your program, right? And make some of those stuff dynamically loadable so the operating system can make these things happen for you, right? And he creates a program, right? How many of you realized all this was happening? And this is for a simple program, right? And obviously, if you have more complicated program, things get more complicated. You might have seen the errors, right? So when you didn't see the -p thread, it complained that it couldn't find p thread creator or what have you, right? That's because if GCC did not know what libraries to add, it can't fail. And when you do a p thread, you should try that. If you do a -p thread, a whole bunch of options will change because it's telling you I'm going to use a p thread. So a whole bunch of libraries will change. The CRT and all those things will change because now it's a multi-threaded application. Libraries will change and all those things, right? This has nothing to do with the operating system. This is how the compiler is going to talk to us, right? Talk to the operating system. Because once you create a program, like after this, you create a program a.out, right? Now a.out is transformed from what you program into a fashion that we as operating system can now see what memory you used and what needs to be dynamically brought in, right? So one of the commands to do that is if you do a LDD a.out, right? That tells you what's the dynamically linked objects into your program. You'll say that you're using two dynamically linked objects. One is libc, right? And this maps into this particular stuff for me. So this is telling me when you go, if you run this program at this moment, this is where I dynamically load these objects, right? This is just for your information, right? So your program now becomes part dynamic, part static, what have you, right? So let's look at how the assembly language looks, right? Hello world, you want to print the string hello world, right? That means your printf has to be given a string called hello world, right? Hello world is a constant, right? You realize that there's a constant. So the constant has to be put somewhere for your program to call, right? So when you're compiling this stuff, you have to put this into some memory location. And when you're actually running the program, your printf can be given this memory location, right? The whole point of the module is we don't know where these things will go at the end. So when you're compiling the program, in this case, right, you don't have to know the exact details, but you can sort of read through the stuff, right? So it says that you're creating, this came from a file called hello.c, right? The first one, .file hello.c. This is, of course, in assembly language, not in C, right? Then it says .section.ro data, right? Which means I'm going to create a next section for read-only data, right? This data cannot be modified. I don't know what that means. Assembly language does not know what it means, but tell the operating system that this is a data that should not be modified. This should be put in a place where the program is not expected to modify, right? It's giving a hint to the operating system that this is a read-only data. It's up to the operating system to deal with it or not, right? But it's saying it's going to be read-only data, and I'm going to call it .lz0 because I don't know where it's going to be, right? I don't know what address it's going to be. It's up to the dynamic linker or loader to actually resolve what lz0 to be whatever, right? So when you're running the program, if the operating system says your program will start from 100 to 200, then the loader will decide that lz0 is really 100, right? But at this stage, you don't know. You just call it this abstract notion called .lz0, which will be resolved later, right? And there's a string called hello world, right? So you're telling the loader that I need a read-only data section, and I need some memory for the string hello world, right? So when you load the program, create this read-only data, copy this variable into it, right? The user is not expected to change it from within the program, right? And if they do modify, I don't know what you should do, but it's up to you, you and the operating system to decide what to do with it, right? And then there's a .text, which says text is a program. So now I'm going to create another section, right? One section for read-only data, and one section for your program. It's called the text, and you're going to have a global function called main, right? And I kind of ignored, there's a whole bunch of assembly language here. And essentially at this point it says I'm push shell, right? You know, the assembly instructions it pushes the stuff in the stack, the arguments. So for the printf, call printf, I'm going to push the value of that section, right? $.lz0 means the address of where that object is, which I don't know what it is, right? So when you do the loading, right, you have to decide where to load the program, but then you have to go and modify my program to replace this unknown stuff to the actual stuff when you run the program. Does that make sense? When you're creating the assembly language program, you're creating the object program, I don't know where it's going to be, so I'm going to call this as .lz0, right, because I don't know what the actual number is. When the loader comes much later in the process, it'll go through your program and make sure that all these will get resolved to the actual number. So if the operating system is saying you're going to load LZ0 and address 100, the loader will go and change this to 100, right? With the hardware support, you don't have to do that. You can make this stuff a lot easier. We'll see what that is later. But essentially, that's what happens. So when you compile your program, your program is in a half-ready state, right? But the loading does most of the stuff for you. So it will do all these resolutions. So and then it will call printf, right? And again, the printf comes from a dynamic load library, like a C library or whatever. And that loads will have to be resolved. So essentially, this is what your assembler produces. And then as things move along, things get linked, things get added, and your program runs, right? So our goal is to make sure that when the assembler says, I want read-only data, I give you read-only data. Our goal is when you say you want a text, I give you a text. The goal is I make sure that all these things are linked so when you run a program, it runs. Our goal is if you're nice, right, if the operating system wants to be nice to you, it can define that read-only data means that it cannot be modified. So within your program, if you try to modify that particular area, it can give you an error. What kind of error do you think it can give you? Many of you may have seen that error. If you try to modify something that you're not supposed to modify, you should try it, right? Let me say, the compiler will complain bitterly if you try to do some of this stuff, right? But nice thing about C is you don't have to listen to it, right? So if you say something like, right. Can you see it from the back, right? So I call character pointer equals hello, right? And hello is a string. So if you think of ANSI C, right? Implicitly this is a constant string, right? Because it's a constant string, right? And when you do a star PTR equals something, I mean here I'm making it null, right? Which is what you're trying to do is you're trying to make this into null, right? What do you think will happen? What does ANSI C say should happen here? Try it, okay. It'll complain that you're trying to modify a constant variable, right? Especially if you do a GC ANSI compiler, it'll say modify it, right? What should happen if you do this? Which may or may not happen, but what do you think should happen? You just learned ANSI C, right? With the constant keywords. Right? So what should happen? You can verify to see if it actually happens. What would happen? Take a wild guess. I think you'll get a segmentation fault, right? You make it a segmentation fault because it's saying segmentation fault says you're violating a segment's, you're faulting on a segment, right? And remember the read-only segment and all those things, I use the word segment, right? So you're telling the program this is going to be in a read-only segment, this is going to be on a text segment, this is going to be on a read-write segment. Segmentation fault really means you're faulting on some segment things that you told me, right? So if your compiler told me that this segment is read-only, now you're violating that, you're faulting, right? You ever wondered why you get the word segmentation fault, right? Because you're violating something that the segment was. You told me through the compiler that this is a read-only segment. Now you're violating it, so I'm going to give you a fault, right? And as you realize with many of these things, you may or may not get the error because the operating system does not have to listen to you, right? If you say it's read-only data, it does not. So the assembler itself may be smart enough to see that you are modifying this. So instead of read-only data, it can put you in a read-write data just because it knows that you're doing something you're not supposed to, but I'm going to let you kind of stuff, right? So that's sort of what happens, right? So essentially, so at this point you have all this data, and you tell the system, and then we see how these things all get mapped, right? So there are multiple ways in which we can do this translation, right? From .lz0 to the real address, multiple ways you can do that. And again, this is all compilers. If you take a course on compiler, this is what you spend in a whole semester, right? So you can do it at the compile time, where when you're compiling the program itself, it resolves it, right? Somebody resolves it so that your program will only run at certain address, right? So compiler may decide that .lz0 will be 43 for whatever reason. That means your program will only run if it was loaded into that exact location, right? So if you assume that your memory was from 0 to 1000, and if the compiler says that the hello world string has to be at this location, right? That means every time you run the program, your program expects the data to be at a certain location, right? You don't expect anything to be modified, right? Which gives you a lot less flexibility, which means that once your program is compiled, if you change anything about the system, you have to modify it. So if you change your system, if you add more memory, your program will not be able to use it because it knows that everything has to be there. But it can potentially be faster because everything is resolved. There's no loading, there's no linking. Things can be fast, right? So can you think of reasons why you would use this compile time loading? Even though it's less flexible, can you think of reasons why you would want no linking and loading, but essentially everything is resolved? Yeah.
Embedded systems.
Yeah. So if you're using like let's say in my watch, right? The chance of me upgrading my memory in my watch is nil. The chance of the vendor modifying the memory is nil, right? They're going to make a million of these things, so they don't mind making a specific version of the software for my watch, which only works on my particular version of the watch. If you add more memory, you have to recompile the program. But it doesn't matter, right? I mean, embedded systems in a car and all those things, right? How many of us upgrade the memory on our car navigation system or car self-control system, right? So it makes the program simpler, but obviously everything gets compiled in and you have this one image and nothing works, right? So probably there are a lot more systems which use this model than the other ones we talk about, because embedded systems there are a lot more embedded systems, right? So the other thing you can do is load time, which is when your program gets loaded into memory, right? So when you call PowerPoint, when you say run a.out, at that time I can do this resolution. And at that time I can say, you're going to run from here, you're going to run from here. Then I replace all these variables such that at the load time, they get resolved, right? But once it's resolved, you're kind of stuck there, right? I cannot move you anywhere because while I'm loading you, I do these modifications. But once it's done, you are stuck there, right? That's one way to do that. The other way is to do it at execution time, right? Which is nothing is resolved, right? All I guarantee is right before you come to the point where you need it, it'll be set for you magically, right? So when you come to that location, LZ0 is accurate. So, but I can modify it any which time I want it, right? So operating system takes a lot more control. So it can move you around as long as it does something so that when you come to the exact point, things will be fine. You as a programmer won't know any difference, but it gives me a lot more flexibility to move you around, because now I can say, I don't want you to be in 100, I want you to be in 200, or I want you to be in 300 or whatever. You as a programmer won't know what is happening. Gives me a lot more flexibility, but it also slows you down because now it has to do all this stuff all the time, right? So those are the two ways you do that. One is like doing loading and one is doing execution time. Each of them have their benefits, each of them have their problems. And it'll become clearer as you move along what those are, right? In general, the more flexible things are, the more complex things get, the more things slow down, and the more the hardware support you need, right? If you get more hardware support, you can do certain things. So one of the things that you as an operating system designer would do is when you're rebooting your system, you try to see what hardware you have. And depending on how powerful your hardware is, you may choose one or the other, right? And that way you can get flexibility if the hardware allows you, or you get the performance if the hardware does not allow you. And those are decisions that you will make along the way. And we'll see what the different stuff is, right? So again, you may not really see what you cannot be able to see the exact symbols here. It's not important what the symbols are, right? All I did was I looked at, so enum is a utility up the top, which tells you what the different symbols are and where they're resolved, right? So I looked at the enum of a.out, which is from the hello world, right? So it tells me, I mean, obviously it goes on and on, but essentially tells you what are the variables in your program which are resolved and where the address is, right? So there are some variables, so there are some things, so these are called word and this is text and so on, right? Again, I'm not going to go through all the detail because this is in the compiler class that you figure out what those are. But essentially, your program has a lot of these things added, right? All those things from the CRT and everything. So your program, this simple hello world program now has all these libraries and stuff. Some of them are resolved. This is not resolved, right? This is still a symbol. Some of them you'll see are in a certain location or what have you, right? So this is all the stuff that is in the A.out that needs to be loading. So when you're loading this stuff, you would resolve some of the stuff to say, some of them is actually in an address, right? So for example, this do global details args, which I have no idea what it is. It's a text. It is in this address, right? A.out resolved it to a certain address. Some of them will be resolved on the fly. Some of them are already resolved. So when you look at the program, right, your simple hello world now has all these symbols, all these stuff, and that's essentially what is happening. And we're talking about how this gets resolved, because you need this actual address to make your program work, right? So in this particular case, it already resolved this particular symbol. Some of them may not be resolved, and they get resolved as things move along. Make sense? Again, I'm not trying to teach you all the compilers in half an hour, but I'm telling you enough so that you can kind of appreciate what is the challenge, right? Because you want the maximum flexibility for the programmer, because you don't want to worry about where these things go, what the addresses and all those things. You just want to program. And you want the maximum flexibility for the operating system, so it can move things around, so it can do all the stuff. It can make bigger programs run on a smaller amount of memory and all those things. And how do you balance these two goals is what is our focus, right? So in terms of the dynamic loading and dynamic linking, right? So dynamic loading essentially means that when I'm loading, so during the load time, I resolve all the addresses, right? And you don't have to load some of the stuff till it's needed, right? You can dynamically load the stuff as you move along, but the linking is already done. So all the actual addresses where they should be can be done is already done for you. The loader process told you that the function printf is going to be at a certain address. It's not actually loaded till you need it. That's the dynamic part. But you know exactly where it should be, right? The linking already happened, right? In the compiler terminology, loading is when you load the program. Linking is when you say that .lg0 is now certain address, right? But when you use the dynamic linking, then you have to do the stuff on the fly. So when your program operating system gives you a new chunk of memory, your linker has to go through your program or what have you, and then modify all the variables to find the right address, right? So this is more flexible, but it needs the operating system to be involved, right? Because operating system has to tell you what addresses things have to be linked, and only when then can you actually link the program, right? So the last collective step happens on the fly, right? Don't worry too much about if you don't understand exact thing, but you just want a broad understanding, because we're not going to tell you how the linking and everything should happen on a linker. We're going to tell you how the memory allocation and all those things will happen from the operating system perspective, right? But here's one plug for you to take compiler class, because compiler is the one which takes a program and can give it something that can talk to the operating system, right? And this is why operating system is a prerequisite for the compiler, because unless you know how the operating system is going to deal with it, you can't just produce code, right? So one of the things you learn soon enough is that if your program can call these addresses, I've been saying like 100, 200, all those things. It can call it in one of two ways. One is the actual physical address. The other is an abstract address that you can deal with, and you can have something modified, right? So if the program was to call it on the actual physical address of what the system has to be, then you don't have much control, right? So if your program says, I want to access memory location 10,000, right? That means if you have memories, if your system which only has 0 to 5,000, you only have 5,000 bytes of memory, right? In that system, your program cannot work because it's trying to read something which is not there physically, right? It may work for the compile time loading system we kind of alluded to, but on a real system you can't really work because the numbers may have to be changed, right? So we introduced the notion of a logical address and a physical address. Physical address, in the next slide it'll become more clear. But essentially what happens is when you write a program, when you call some address, it's called a logical address, right? And on the fly, we translate that into a physical address that actually maps to the actual address. And we do that because we have a lot more flexibility, right? So I'm going to skip one slide. And this is essentially what happens, right? What it means is when from your program, if you call a variable like 346 or something, with the physical logical split, I mean, this is, again, from the hardware folks have to help you. But essentially, one simple way to do that is to do a simple translation such that when you say 346, I add some number 14,000 so that on the real memory, your particular address is really on 14346. So every time you call some memory location, I will translate it through a simple scheme or whatever scheme. So you as a program would only see the logical address, and the hardware only sees the physical address. And every address you see will have to be, you have to add this translation, which means the operating system can put you wherever, right? So you as a programmer would say, my program starts from address 0 to 10,000, regardless of what machine it is. I can put you on the different slot, like remember the colored slot, right? I can put your program starting from 1,000, yours starting from 2,000, somebody else from 3,000. Within your program, you always assume that you're running from 0 to 1,000. So you call a number like 346, and every time I do a translation from 346 such that on the physical memory, it goes to the right spot. So if you have multiple programs, they can all be disjoint. They don't overlap with each other. And if you do this translation right, then all the programs assume that they're running from 0 to 1,000. On the real memory, they are running at a different location, right? And this addition has to happen, right? This is in the critical paths. Every address will have to go through this critical path, right? So if you do this in software, your system will be slow as a dog. So you need this thing called memory management unit, which does this translation for you in hardware speed, right? And the operating system goal is you can modify those, right? You can modify the 14,000, nothing else. If you perform this addition in software, every operation will be slowed down, right? Before I answer the question, let me point out a case of where that affects you, right? So if you did A equals B plus C, right? Simple enough, right? In your program, B will be in one address, C will be in one address, A will be in one address, right? So if I have to do this translation every time, A, I'll have to do whatever A you think it is plus the physical address, B, whatever you think it is plus physical address, C, whatever you think is plus physical address. So it's a addition, and addition here, right? So if you were to do this in software, your program will be extremely slow because this will take 4 additions rather than 1 addition, right? You don't feel the pain because you have this memory management unit which does this for you practically for free, so that this addition, you don't actually notice it. It happens for you, right? Yeah.
Do you mean that the program depends on it being a certain logical address because of how it's compiled or how it's actually written?
How it's actually compiled or loaded.
So it's the way it's compiling it that makes it depend on the address.
Yes.
Okay.
So when you compile it, like in the assembly language, right? It has to say L0, right? It does not know what L0 is at the assembly language, but when you're loading it, that L0 will have to be translated to some number, right? So let's say 100, right? This lets you change it even as the program is running. I can change wherever it is, right? So even though the L0 you think it's 100, I can, depending on how much I change this value, every time your operating system moves you around, right, your program will still look like it's working the same, right? Your program wanted something in LG0. LG0 was resolved into 100 during load time. But even when you're running, things get modified all the time, right? It'll become more clearer as we do why we do this. Every time you context switch, you have the freedom to move you around, and you won't notice a thing, right? So you may be running on this location for a second, then I may move you somewhere around, and you as a program wouldn't know any difference, right? Right? But the key thing to remember this: you need hardware support, and that was the previous slide. You always think of logical addresses. Physical address is all that is needed, and the magic happens by MMU. If you don't have MMU, your system would be slow, but most modern operating systems will have MMU, right? And we'll continue with that, but as you'll see, that MMU will get more complicated as you go along because you can do a lot more stuff, right? So this model depends on the MMU, which is hardware component, which makes us do the cool things, right?